Here's a solution to one of the online homework problems. This is getting at the distribution of the X bars that we talked about in class on Tuesday. So in this problem, we are told the distribution of weekly income among farm workers, and we're told that the mean weekly income is $500 and the standard deviation, and this population is $209. And so, so a researcher who doesn't know those things, of course that's kind of the point, is we don't really know this population numbers, is going to randomly sample 121 farm workers and compute the X bar, the mean of that sample. And so the way we think of this is we imagine that a bunch of researchers all have the same idea and all go randomly sample 121 farm workers. And so we imagine a situation where there's lots of X bars that are being calculated, all based on different random samples of 121 farm workers. The theory tells us that if that's what happens, then we'll have a distribution of the X bars that all those people get. So we draw this on the worksheet. I label these X bar distribution. Let me put that down a little lower. So this, and so this distribution, because the sample size is at least 30 and the original data, we actually know the theoretical sigma in the original data, whether we know we do or not, we actually will have a normal distribution. So we don't have to worry about the t distribution stuff for this. So in 7.2, you're always assuming that you have a normal distribution. The theory tells us that this X bar distribution should be centered on the same mean that the population is centered on. That is, if a random person has income $500, then if you go ask a whole bunch of people and compute their average amount of money per week, that also should be typically $500 and can be up or down randomly from there. The 3 tick marks that we put on our normal distribution, each tick mark is going to be based on the standard error. And so standard error formula is sigma over the square root of n. So in this case, sigma is, where to go, 209, and n is 121. So 209 over the square root of 121, that's 19. So it comes up to be a nice whole number. And so in the X bar distribution, again, remember this is the distribution of these means of 121 people each. This is going to be distributed according to this normal distribution labeled like this. So 519, 538, 557. That's going up by 19 each time. If I go down by 19 each time, I'll go 481, 462, and then whatever's over there. So that's what the X bar distribution looks like. So that means that if a whole bunch of people go out and collect 121 answers to the question of how much money do you make each week, and they all calculate an X bar, they bring them back together, those X bars are going to look like this. They're mostly going to be in here. They're mostly going to be between 480 and 520. Occasionally they'll be out this far, and almost all of them are going to fit somewhere on there. And so ones out here like a $600 average would be really unusual, or a $400 average would be really unusual. So we get a sense for how these X bars could be, which ones are reasonable to happen and which ones are would be unusual to happen. Okay, so so this explains why it's almost certain that the sample mean will fall within whatever. This is based on our empirical rule, right? All of these are about the empirical rule. And remember, in the empirical rule, it said almost always the value will fall within 3 standard deviations of the mean. And so this 57 is not just coming out of nowhere. 57 is actually 3 standard deviations. So here's 3 standard deviations above. That's 57 above the mean, and then 57 below the mean will be whatever this guy is. So I just ran out of room there, but what was that, 443, I guess. Anyway, but the empirical rule says if we have this kind of data, this symmetric bell-shaped data, then almost everything falls within 3 standard deviations of the mean. And so that's all this is saying. So the empirical rule says that if we're bell-shaped, then all or nearly all fall within 3 standard deviations of the mean. And 3 standard deviations is 3 times 19, which is 57. Okay, so that's all that is. And we had that on the worksheet. I asked it the other way around. I just said, what are the two numbers that we get within 1 standard deviation, 2 standard deviation, 3 standard deviation? But this question is what that worksheet was based on. Okay, now finally, part C asks us to actually find a real probability. So the probability that an X bar, if you go off and find one, what's the probability that the one you find is within $23 of mu? So in other words, the mu is the middle. So within $23 of mu means between about here and about here. Right? In fact, I don't have to say about. I know exactly where this is. This is 523. That's $23 above the mean. And this is 477. So within $23 of mu is the same thing as saying, I want to know what's the probability that I get an X that's between 477 and, an X bar is between 477 and 523. Right, that's what it means to be within $23 of the mean, between $23 below the mean up to $23 above the mean. So when I'm asking a probability question or a proportion question like this, I'm actually asking for this area, and that's exactly what our normal CDF function tells us. So this probability is equal to the area that's shaded, and that's going to be normal CDF on a calculator, normal CDF function of the calculator. We can tell it where to start shading, where to stop shading. So that's what our normal CDF function looks like. Just tell me where you want to start and where you want to stop, going left to right. So starting at 477 and shading, shading, shading up to 523. So that's what those numbers are. What we learned on Tuesday was that the normal CDF function can actually take two more arguments that tell it what curve we're looking at. So the thing that determines which normal curve you're using is the center and the size of the tick marks. So the center is 500, and then comma, and the standard error, in other words, the length of the tick marks, is 19. So if you put 4 numbers into normal CDF, it will actually find this area for you without you having to convert everything to z-scores. When we worked with proportions, we deliberately converted the picture to a z-score picture so that we could use our table and then also use the normal CDF function without these extra 2 numbers at the end. And we didn't have to do that, but we did it at the time so that we would build an understanding of the connection between the value observed and the z-score, because that is an important idea. But you don't have to make that conversion in order to find the probability. The normal CDF function takes 4 numbers, where the first 2 have to do with where your shading starts and stops, and the second 2 are the parameters that determine this curve, the center and the standard deviation. And so if we do that on a calculator, TI calculator, then we get this 0.7739. If you are determined not to use a TI calculator, then your only other option is to change this picture, take this entire picture, and change it to a z-score picture. In other words, redraw it, so that the center is at 0, a 0 z-score is the middle. Figure out on either side where these lines are going to be. So to find this line, I've got to find the z-score of that value. So the z-score over here is going to be 523 minus 500. In other words, the observation minus the mean over the standard deviation. So that's going to be the z-score of that value. A similar calculation will tell you the z-score that corresponds to this, 477, it'll be negative. And then we can just use normal CDF between these two z-scores, and that would give us the same answer. So normal CDF allows you not to have to push the problem back over to z-scores. If you're going to use the table, then you have to use the z-score values. But it's not different than what we did before.